Hello everybody and welcome back to my channel. Today we are going to talk about weak acid, pH and pKa. This video is going to be built upon the last video I did, ion trapping mechanism. And stay tuned because next video I will be talking about weak bases, their pH in relation to their pKa. So this is just to give you an overview of what we are doing in anesthesia when it comes to pharmacology. These are the application of the ion trapping mechanism concept. So if you haven't watched that video, please watch it first and then come and watch this one. So without further ado, I'm going to be using my tablet to read the question. I will make sure I put all the variables on the board so we can go together, we can read it together. Weak acid, we have a formula that links the weak acid in regard of pH and pK. So for the weak acid, pH equal pK plus log of the ionized form of the acid over the non-ionized form of the acid. So how are we actually using this formula? I'm gonna go through some questions and we're gonna answer them together, and I will show you the method I use. Everybody uses different method, but this one has ever worked for me. So we have a problem. Aspirin, which is also called acetyl salicylic, is a weak acid drug that has a pK of 3.4. So AAS pKa 3.4. Now we are asked what's the ratio of the ionized over the non-ionized when the pH is equal 7.4. So we want, in other words, what is the percentage of non-ionized and what's the percentage of ionized of aspirin when it's in environment with the pH of 7.4. So I'm just going to plug in my variable into the equation. pH 7.4 equal to 3.4 plus log of the ionized over the non-ionized aspirin. So if I move my variable, because I'm right-handed, makes me do better. So the log of the ionized over the non-ionized is equal to 4. Now I'm trying to get rid of the log. To get rid of the log, I'm gonna raise 10 exponent 4, which is equal to 10,000. So from here, I already know that I have 10,000 times the ionized form versus the non-ionized form. This is actually a ratio, but what I'm asked is the percentage. So what's the percentage of 10,000 and what's the percentage of 1? So 10,000 plus 1 is going to give me 100% of the drug because I have 10,000 ionized and 1 non-ionized. So 100% of the drug is 10,000 plus 1. So what is the percentage of 10,000? So the math of this is going to be, if I plug in all my variable, it's going to be 99.99%. So 10,000 represent 99%, which is the ionized form of the drug, and 1 is just going to be 99.99 minus 1, which is 0.01, which represent the non-ionized form of the drug. So I have 99.91% of the ionized and I have 0.01% of the non-ionized form of the drug. Now if you look at the problem, if we were only asked if aspirin will be in more ionized or non-ionized with a pH of 7.4, we wouldn't have gone through the whole math question. It was actually going to be easy because I have pH 7.4 is less than the pK of aspirin 3.4. That means I am in an alkaline environment. So because I have a weak acid, aspirin, and I know that acid work better in an acidic environment, that means in my alkaline environment, my acid is not going to work better. And my acid for not working better, that means I have more of the ionized portion because the non-ionized is the active side of the drug. So I would have known that more of my aspirin will be in the ionized because acid does not work better in an alkaline environment. So this is just some trick to remember. Acid works better in an acidic environment. Basis works better in an alkaline environment. So let's move to the next question. So we're still gonna stick with aspirin with a pKa of 3.4. Now what will happen if our pH drop to 1.4? If our pH is becoming more acidic? From right here, we have a pH less than the pKa. So we know we are in acidic environment and our acid work better in an acidic environment. So we already know that we're gonna have more non-ionized drug. But because we are asked of the percentage, we have to go back and use the formula. So I'm just gonna plug in my variable. It's gonna be the same thing we just did, plus log over AH. So for the purpose of the video, I'm gonna make it a little bit shorter. So log of A minus over the non-ionized portion of the drug is gonna be -2. Getting rid of the log equal 10 to equal 0.01. So if I go back to the same way I did this to get the percentage, so I will find that 0.99% of my aspirin is gonna be in the ionized form, while 99.01% is gonna be in the non-ionized form, which confirm what we have here. So I can actually double check my math that I did the right thing because I know that this environment is acidic. Aspirin works better in an acidic environment because it's an acid. So I'm gonna have more of the non-ionized form, which is the active side of the drug. And here my math just confirmed that, so I feel confident about my result. Let's move to the next one. This is a whole different question. So I'm gonna wipe this down. So now this is an actual problem, and all the questions are going to be built on top of each other. So I have metal hexatol sodium, and I'll call it M. It's just I'm not used to the long names yet. Metal hexatol sodium, which has a pKa of 7.9, and we have a pH solution of 10.5 after constitution, and we are asked of the percentage of the ionized versus non-ionized of metal acetal at that pH. So here, like we said before, pH is greater than the pKa. So we know that metal acetal is a base and pH is greater than the pKa, so we are in an alkaline environment. Metal acetal is a weak acid and we are in an alkaline environment. Acid works better in acidic environment, so I know from here that my metal acetal is gonna be in the ionized form more. So let's plug in the variable. pH 10.5 equals 7.9 plus log, same thing. So we get to the log of the concentration of the ionized over the non-ionized. When we do the math, it's gonna give us 2.6. So non-ionized over the ionized is gonna give us 2.6, which is gonna be 398.1. So by doing the math, it's gonna give us the proportion. Putting this number into percentage like we did the last time, it's gonna give us 99.7 over 0.3%. So I actually have more of my ionized, like we said here, than my non-ionized 0.3. So this is actually true because we are in an alkaline environment and acid does not work better. So more of the ionized drug is gonna be present, knowing that it's the non-ionized drug that is actually active. Let's move to the next question. What would happen to metal acetal solution if it's mixed in the same syringe or prepared simultaneously during IV infusion in the same line with atropine sulfate, who has a pH of 3.5? So if we mix atropine, which has the pH of 3.5, with metal acetal has a pKa of 7.9. Here we are in an acidic environment because the pH is less than the pKa. And what do acids do? They work better in an acidic environment. So in this environment, metal acetal is going to be more in the non-ionized portion. So this is just how we process the information, and you also have to work smarter and know it by hand. It makes it easier. So the next question, assume normal physiological pH equals 7.4, pH 7.4. What will happen to the fraction of ionized and non-ionized molecule if metal hexatal is administered at a pH of 7.7? So now the question is just asking if we move to a physiological pH, which is 7.4, to a more alkaline pH, which is 7.7, what will happen to metal acetal? So now we're given another pH 7. We are told that we're moving from a pH of 7.4 to a pH of 7.7. So our environment is becoming more alkaline, and we want to know how metal acetal is going to react in a more alkaline environment. It's just like a patient who is losing all his acid and you're giving him methotrexate, what is gonna happen? This is just scenario. So because we're moving towards an alkaline environment and methotrexate is a weak acid, and we know that weak acid work better in an acidic environment, so methotrexate is gonna be in more ionized portion because the environment is becoming alkaline. So the next question, based on your answer on the previous question, what will happen to the speed of induction? The ionized portion is the portion that is easily excreted, is water soluble, is not active, so the speed of induction is going to be slower. So next question, now assume the normal pH is 7.4. What will happen to the fraction of ionized and non-ionized molecule of methotrexate sodium if administered to a patient at the pH of 7.2? Now we're moving to an acidic environment, 7.4 pH to a pH of 7.2. Methotrexate is a weak acid. It works better in acidic environment. So here it's gonna be more in a non-ionized because it's the fraction of the drug that is active. And what will happen to the speed of induction is gonna be faster. Okay guys, so this is what I had for weak acid. I am going to upload a video for application on weak base. So stay tuned. If you have any question, any suggestion, any comment, please feel free to write a comment below. And also like and subscribe. Thank you very much.